Yeah, Max Gillett. I guess I'll be talking about optimal zkVM design. It's sort of a provocative title, I guess, but these are, again, it's more of a kind of brainstorming talk coming out of sort of discussions with other members at Delendum and trying to work through some of like the design goals and challenges, high-level design goals and challenges of what we're trying to optimize for and what this looks like from a developer experience point of view. So yeah, I mean, first, what do we want to optimize for here? I think, 10 years ago, the TinyRAM paper sort of said it best. We want to kind of decrease the circuit complexity of our transition function. And we also want to, basically limit the number of instructions that we're actually having to execute the cycle count. And I think not much has really changed 10 years later. So, right, this is performance in a zkVM setting, particularly a Stark-based one. I mean, this is essentially, we want a small execution trace, and we want low-degree transition constraints. But there's actually other things we want to optimize for here. One is productivity, right? We want this zkVM to support most high-level languages. We don't want to ask the developer to code in some custom language that requires some new learning curve. We want to be able to leverage existing libraries of code as part of that. And I think what goes hand in hand actually with productivity is security, right? Rewriting code introduces the opportunity to add new bugs. It's also very time-consuming and expensive to just audit translated circuits and rewritten code. So one solution is like maybe just targeting a common instruction set architecture. So I mean, this seems to accomplish both our goals of productivity and security. For example, we can just write in Rust or Go and compile down to a RISC-based instruction set, feed that into the zkVM. But the problem is that modern CPUs, even those with reduced instruction sets, were not really designed for zkVMs and sort of make assumptions that don't really hold in that context. So like one assumption is just memory access latency, just partially due to just the physical distance between RAM and CPU registers. Other things like speculative execution, multi-threading, list sort of goes on here. And the architecture of CPUs resemble really nothing of zkVMs. Like we don't really have this concept of like caches in the real sense. So one problem, just an example here, that targeting like these common ISAs gives is this register allocation problem, right? So in a zkVM, there's actually no performance gain to be had by reusing registers. This was the case, 10 years ago in the TinyRAM paper, in the TinyRAM system, because you had this register routing problem. You had a situation in which memory access was actually n log n, but we now have permutation arguments, and memory access really costs a single cycle. I mean, there's still some sorting that needs to be done that can be n log n, but this is much faster than kind of actually writing a circuit here. So yeah, general purpose registers really add two sources of overhead in the zkVM. We have to have an execution trace, so we have to record what these registers were at every execution cycle, regardless of whether they were actually used. This can be in the form of just extra columns in our execution trace, or it could be we just have a larger evaluation frame for our VM, and we're packing traces, we're packing registers into those frames, so we're increasing the number of rows. And we're also sort of wasting execution cycles on instructions that are just spent essentially rearranging, register values are loading into or out of memory when we could just operate on the memory directly. So yeah, we can get around this with some, like, I guess, microcode optimizations here, in the sense that we can translate the decoded instructions into a more friendly representation. So for example, like a hypothetical example here, we could come up with a register table where we only keep track of the changes. Well, first of all, we dedicate the first kind of 8 rows of this new table. We just set the register, in this example, 8 registered values to 0. And then each time we use a register, we just actually append a single row that basically with constraints that the previous register and the current register sort of match up using a permutation argument here. Or in the previous access, yeah. So this minimizes the trace region dedicated to representing registers. We no longer have to maybe have, if we have 32 registers, we don't need 32 columns. We just need to have as many columns for this kind of register table. But it doesn't really eliminate the unnecessary cycles spent managing these values. So these, we still have to introduce sort of wasted rows in our main CPU trace. And also, I mean, sort of by definition here, like we've already decoded the instruction, we can't eliminate the overhead like involved in that actual decoding. So even in like a simple RISC-based architecture, instructions can be complex. Like you can have immediate values of different lengths here, and like this just adds additional overhead both in the trace and constraints. We could think about actually translating like the instruction set to something that's more zkVM friendly, but it's sort of difficult to reason about high-level operations after we've already lowered to machine code here. So instead, I mean, we can think about targeting an intermediate representation, which is sort of one step above machine code. It's used to help with code generation for machine code. There's basically 2 widely adopted IRs. There's LLVM, and there are also IRs built to actually run WebAssembly outside of JavaScript, just on a native machine. So in Rust, this doesn't require any changes to the compiler. It's already kind of baked in, like Rust source code compiles down through a couple different IRs, including LLVM before machine code is generated. Similarly, WASM can just be, we just pass a flag during Rust compilation to target WASM. There's no kind of forked tooling that we need to download here. And the idea is that we don't target the IR directly. This isn't like zkWASM or zkLLVM. We're just using this intermediate representation to generate kind of zk-friendly code. Because the LLVM instructions and WASM instructions, like the same argument can be made. Like those weren't optimized for a zk setting. They make different assumptions. And as I mentioned, importantly, this requires sort of no modification of the source compiler toolchains. So just a comparison between LLVM and WASM. LLVM has a small number of instructions, but IRs, for example, crane lift IR, which is very popular to generate WASM, translate WASM to machine code, has a large number of instructions. There's what are called like function intrinsics, things like multiplication of 2 64-bit integers or 128-bit integers. Like LLVM has like custom like intrinsics that show up that are in the code to sort of represent these instructions. The WASM IRs are a bit simpler. They don't have these, so you just need to deal with instructions. It's sort of more streamlined. Differences in language, LLVM, right, it was built in C++, a lot of the tooling is C++ based. The WASM IRs generally are built in Rust. In both cases, we actually have a nice representation called static single assignment where the code is all register-based. Right, WASM is a stack machine, but when you translate it to an IR, it becomes register-based. But yeah, there's some more nuances here, like in terms of stability and target dependence. It's not obvious kind of which IR to target here. In the interest of time, I'm just going to skip over, and I'm also not even sure anyone can see it because the color scheme here is not great. But I had an example just sort of showing what LLVM code sort of looks like and making the case that, right, you don't want to compile down to machine code. You've sort of lost high-level information. But yeah, just to get into some of like the design considerations for what the zkVM instruction set should look like. Right, we first need to recognize that really no ISA fits all programs. And we actually want more of like a principled approach to just develop a set of ISAs. And so this set basically would consist of just like a simple, base instruction set that has numeric and control flow instructions. That's represented as sort of main CPU trace. And then we want sort of a more modular, like table-backed instructions. So these would be in separate tables, separate starks that the main trace communicates with through permutation arguments. And these things, can handle hash functions, wrong field arithmetic, elliptic curve operations, and so on. And right, to add an additional coprocessor, this table, to access it, we really just need to add like an extra, additional instructions in the main trace, which is not difficult to do. So what is like the developer overhead? Right, so I think we can like categorize programs into those that are kind of cryptographic in nature and basically everything else. And so, like, for programs with cryptographic operations, we kind of want high-level architecture independent instructions. Like, a lot of the code right now for pairings and, like, even low-level field arithmetic, right, it's been heavily optimized for, like, x86 or, like, a particular instruction. We kind of want to replace those functions. We don't want to just translate that to like dumb machine code. We actually want to replace it with like potentially a customized instruction that would call out to one of these tables. And so the way to do that is to basically ask developers to replace libraries with those that, they're still written in Rust. Like the code is not any different, but the library functions are basically forced to not be inlined. So they have identifiers that we can sort of pick out. Right, during code generation, we just want to identify those function bodies, replace them with the appropriate VM instructions. And right, these libraries, it should also be the case that like their functionality and the interfaces like conform to the VM spec. Like if you have a catch-ack function, it should have like the same parameters as the what's going on in like the trace generation for that catch-ack hash table. And just for general purpose programs, right, we should strive for no external import requirements, which I think is doable here. Yeah, and so I think, just to wrap up this final slide, like the process here I think is program-driven development. So, right, a motivation for this new VM that I sort of forgot to mention is that we want to do things that are currently infeasible. Like we want to, basically just plug in a Rust verifier for some proving system, or like beacon chain consensus, or some like light client from some other blockchain, and make very minimal changes to the code. So I think the way that we arrive at these instruction sets is actually through like an iterative benchmarking. So we first obviously have to instrument the program using these external libraries that I mentioned, like they basically prevent inlining. And the second step is we actually execute the lowered code for a candidate ISA. We have this LLVM in which we sort of tagged all the potential like functions that we might want to kind of represent with special instructions, but for the time being, we just lower to maybe a base instruction set. We then actually like count, what fraction of cycles were sort of spent maybe on wrong field arithmetic or like elliptic curve operations, et cetera, and then decide, in the next step, which is sort of optional, do we implement a new instruction and the associated code generation, from that IR, to represent this instruction, or is the performance fine with just using the base set or the existing set of complex instructions that we've already implemented? We just go back to step 2 after implementing a new instruction and test again. Sort of does this make sense to add a new, keep adding new instructions? So that's it.
Any questions for Max? All right, I'll throw out a question, okay. Which is that, do you think we actually need registers?
I think we need, so we definitely need like special purpose registers, obviously, for like program counter, like a stack pointer maybe, and I guess, some more recent discussions since I put together these slides, we might need, we probably do need additional columns within the main trace to sort of enable these memory arguments. I guess you could call them registers, but they're really going to just represent, if we have 3 operands and like an instruction in our set of instructions, we just have like 3 registers that basically hold those operand values, which could be either like memory values or pointers to memory. So we'd still need like a small number of registers, but I think it's dramatically lower than like the 16 or 32 sort of register counts that you have in something like MIPS or RISC-V, and so there's performance to be gained there.